Okay, so good evening, everybody. We are ready to begin, and I know it was a little bit weird coming in with no sound, with all the muting, but here we are. If you can hear me, you are good, and you'll be able to hear the others during the presentation. So I'm Amanda Stone with UNH Cooperative Extension, and I would like to welcome you all to the webinar this evening. It's wonderful to see so many people. We have around 62 people who are signed up. Many people are still coming into the webinar. So we're really glad that you were able to participate by having this as an online session. Clearly, webinars are popular right now with the number of people we have, and we really appreciate the interest. In this evening's program, we're going to be exploring the newly released, hot off the press, Coastal Flood Risk Summary Guidance Document, Part 2, as well as reviewing the Climate Science Part 1, released in 2019. So if I could have the next slide, please. Just a quick logistical issue. If you take a look, for those of you not familiar with Zoom, if you take a look at the top right-hand corner of the screen where you'll see the arrow at the top of the circle, make sure you click on speaker view, and that way you only see the person speaking and you don't see all the 50 or 60 people on the webinar, and that just makes it a little bit cleaner and clearer for you. When you click on speaker view, the words will change to gallery view, but that's okay. So to start off, we have a quick poll to ask what interests you most about the coastal flood risk guidance. We're going to pop that up now. You can see it. Just select the answer that best applies to you. We're going to give you 30 seconds to respond. Don't be shy. Just click on one thing. It's anonymous, and we can just see the collective responses as you all respond. There we are. We've got several people. Possible requirements for state and other permitting is at the top of the list. Vulnerability and options for my community is the next one on the list. So we've got some, and then vulnerability and options for one more places that I care about. So thank you for taking the poll. So I'm going to move on to a few technical details, still with that image that we have on the screen. I just wanted to go over some of the technicals. Because we have so many people on the call, as I mentioned earlier, we have muted all the participants. So yes, it does mean that you aren't able to talk, but we will have an opportunity for you to provide questions and comments via chat. But by muting you, it reduces feedback and external noises. We've also turned off video to preserve bandwidth, since everybody is taking this webinar from home. So please be sure to leave your sound and your video turned off. If you have questions or comments during the program, if you go to the bottom of this slide that you see here, you'll see that there's the chat box. There's a little chat balloon, show it with the bubble, and then the chat box will open up in the box alongside the screen. You can put your chat in the little box down at the bottom of the bar, and at the top of the bar you'll see additional chat from everybody else. So you can see other people's questions getting posed. So keep the chat bar open during the presentation. We are recording the webinar, and we will post it to the Coastal Adaptation Workgroup webpage so you can review it later. So you'll receive a copy of that. If I could have the next slide, please. So these trainings are hosted by the New Hampshire Department of Environmental Services, Coastal Program, Piscataqua Region Estuaries Partnership, UNH Extension, and New Hampshire Sea Grant, and funded by NOAA under the Coastal Zone Management Act in connection with the New Hampshire Coastal Program. So there are 5 of us on the organizing team. You can see us all on this slide. You've already met myself. Abigail Lyon with PrEP is monitoring the chat box. So keep the questions coming throughout the presentation. Abigail's going to be monitoring that, keeping track of the questions, and they'll get answered after the presentation. And any questions that we don't get to will be addressed in writing afterwards. We'll be sending out a kind of an FAQ with those questions and answers. So we will get to all of them, but maybe not all during the webinar. Lisa Wise with UNH Extension and New Hampshire Sea Grant is monitoring technical issues. So if you have any technical problems as we're going through the webinar, please put a message in chat and Lisa will work to try to address that for you. And then our presenters tonight are Nathalie Morison, Coastal Resilience Specialist, and Kirsten Howard, Coastal Resilience Coordinator, both with the New Hampshire Department of Environmental Services Coastal Program. And I will now hand over to them to start the presentation.
I'm Nathalie Morison, and thank you all again so much for joining us virtually this evening. I sincerely hope that everyone is staying safe and healthy during these challenging times. As Amanda mentioned, we're here to give you an overview of the 2019-2020 New Hampshire Coastal Flood Risk Guidance and Science. And tonight's session is really geared towards a municipal and professional audience. So we're going to start by giving you some important background and context as to why we're here talking about this. And then we'll jump right into some of the key scientific findings from Part 1 Science, followed by a deeper dive explanation into Part 2 Guidance for Using Scientific Projections. Then we're going to end with a Q&A with questions from all of you. So again, another plug for you guys to just submit your questions in the chat box as they come up throughout our presentation, and we'll get to those later on. So with that, I'm going to turn it over to Kirsten to introduce herself and say a few words before we get started. Kirsten.
Hi, everybody. I'm Kirsten Howard. Before we get rolling, we also wanted to acknowledge that we do really want to conduct some trainings in person where we would have dinner provided to you, and there would be interesting and thought-provoking discussion, and you would all come away with a really good understanding of this product. Unfortunately, for obvious reasons, that's not feasible at the moment. We have every intention of conducting more detailed trainings in the future. For today's session, just keep in mind we're only here for an hour and there's a lot to dig into, and we're definitely not expecting to get through it all in a lot of detail today. So this is really just the start of the learning process that will be evolving based on your feedback and based on the health crisis over time. At the end of the session today, we'll ask you what other forms of training would be helpful on this product, and so give that some thought as we go.
So starting with some background and context, the 2019-2020 Coastal Flood Risk Summary was prepared to fulfill the requirements of state statute RSA 483B Section 22, which directs the New Hampshire Department of Environmental Services to get a group of state agencies together to supervise updates of storm surge, sea level rise, extreme precipitation, and other relevant coastal flood risk projections at least every 5 years. The 2019-2020 update replaces the first edition that was released in 2014 as part of the New Hampshire Coastal Risk and Hazard Commission effort, which I'm sure many of you on the line are familiar with. Development of the 2019-2020 summary was overseen by a science and technical advisory panel that was comprised of key state agencies, the University of New Hampshire, both Stratford and Rockingham planning commissions, as well as representatives from some of our coastal municipalities in the state and the New Hampshire Coastal Adaptation Work Group. The panel met fairly regularly over the course of 1 year and was informed by a group of science advisors, local technical experts, as well as the public throughout its process.
So the 2019-2020 New Hampshire Coastal Flood Risk Summary is made up of 2 parts. Both documents are available at the links shown on this slide. Part 1, Science, was released in August of 2019 and provides a summary of the best available science relevant to coastal flood risks in New Hampshire, including updated projections of relative sea level rise, coastal storms, sea level rise induced groundwater rise, which is new, and precipitation and freshwater flooding. Part 2, Guidance for Using Scientific Projections, puts forward a set of guiding principles and lays out a 7-step approach for incorporating updated coastal flood risk projections into private, local, state, and federal projects that involve planning, regulatory, or site-specific decisions. The primary purpose of the guidance of Part 2 is essentially to make it easier to use the science provided in Part 1.
So we're now going to share some very high-level findings from Part 1 Science, with the big caveat being that neither Kirsten or I authored this report, nor are we scientific experts. So if you have any technical questions that come up related to the science that we're unable to answer this evening, we will gladly forward those to Dr. Cameron Wake and the rest of the science authorship team, and we'll get their responses back to you in writing as soon as possible. So with that, I'll turn it back over to Kirsten to kick off the science.
Okay, so part one starts with a summary of sea level rise science. It states that relative sea level rise, which is often given the acronym RSLR, and which is the localized sea level rise for a specific area, in this particular case, coastal New Hampshire, is rising and is projected to continue rising for the foreseeable future, beyond the year 2150, which is the extent of the timeline on this particular chart. The chart shows historic relative sea level rise from the Portland and CB Island gauges in the thick black line. It shows satellite relative sea level rise observations in the thin black line. And then it shows a range of possible future relative sea level rise if you assume that we follow a future scenario where global greenhouse gas concentrations are stabilized by the end of the century. That scenario is often referred to as representative concentration pathway, or RCP 4.5. Next slide. So to break the projections in the chart down a bit more for you, under that scenario where global greenhouse gas concentrations stabilize by 2100, RCP 4.5, the report states that using the year 2000 as a baseline, we're likely to see up to 1.3 feet of relative sea level rise by 2050. And though less likely, we could exceed 2.9 feet by 2050. We're likely to see up to 2.9 feet of relative sea level rise by 2100, and it's less likely but possible that we'll exceed 8.7 feet by 2100. By 2150, we're likely to see up to 4.6 feet of relative sea level rise, and though less likely, we could exceed 18.1 feet. So here are a couple of really important things to note. Uncertainty rises as we get further into the future. So basically we know more about what the world is going to look like in the next 30 years, and much less about what the world is going to look like in 100 years. So that's why there's such a big possible range in 2100 and even bigger in 2150. Also, if you prefer to make the assumption that global greenhouse gas concentrations don't stabilize by 2100, that they keep increasing, then the relative sea level rise projections are higher. And one scenario depicting a future with higher global greenhouse gas concentrations is referred to as RCP 8.5, and more information is available on that particular scenario in both part 1 and part 2 of the report.
So when it comes to coastal storms, on the other hand, projected changes remain fairly uncertain. Although the report does state that the number of intense hurricanes, extreme hurricane winds, and hurricane precipitation are all more likely than not going to increase by the decade 2080 in the North Atlantic Basin. However, much less is known about the future of nor'easters, which we all know can have a devastating impact on our New Hampshire coast. That being said, it is virtually certain that sea level rise alone will lead to an increased frequency and intensity of coastal flooding associated with coastal storms as the century progresses. As shown in the figure below, coastal storms that occur on top of higher sea levels will result in increased flooding extent further inland and depth, regardless of how coastal storm frequency and intensity changes in the future. Next, part 1 science also explains that groundwater levels are expected to rise as sea level rises in areas up to 3 miles inland from the coast. As shown on the figure on the right, groundwater levels are expected to rise as a percentage of sea level rise, with the magnitude of that rise generally expected to decrease the further you get away from the coast. Note, however, that this figure is not showing flooding resulting from groundwater rise. Whether projected groundwater rise is going to result in flooding is largely going to depend on the present day depth to groundwater. Finally, Part 1 Science describes how extreme precipitation is going to increase under various future scenarios. There are a number of different rainfall metrics that you could look at that help tell this story, so I've just highlighted a couple of those below. The graph on the left shows by the end of the century how the amount of precipitation falling on the wettest day of the year is projected to increase by 8 to 15% at various locations throughout the state if we follow that RCP 4.5 pathway, or otherwise if global greenhouse gas concentrations stabilize, which is depicted in the blue curve. On the right-hand side, the graph shows how by the end of the century, the number of 48-hour or 2-day storm events per decade that produce more than 4 inches of rainfall is projected to increase 64 to 77% at various stations throughout the state if global greenhouse gas concentrations stabilize, again depicted in the blue curve. One thing to note, though, is that the percent increase in both of these metrics is higher if global greenhouse gas concentrations continue to grow, which is pictured in red in both graphs. So keeping these scientific findings in mind, we're now going to shift to explain Part 2, which, as we mentioned earlier, was released just last week. And the purpose of Part 2 is really to help decision makers like yourselves use the science that's presented in Part 1. It's directed at decision makers in all 17 of our coastal zone municipalities in New Hampshire, but the precipitation information that I shared with you earlier is definitely relevant statewide, so that's important to keep in mind. It's also important to note that use of this guidance is strictly voluntary, but that it or parts of it could be required by various state and local regulatory authorities in the future. The guidance includes 9 guiding principles for how to incorporate coastal flood risk projections and decisions, a 7-step approach to help you select the coastal flood risk numbers to use in your projects and identify management strategies, as well as a few case studies to help illustrate how this type of coastal flood risk information has been used in our state to date. We're briefly going to go over the guiding principles and the stepwise approach with you today.
All right, so the 9 guiding principles are listed here and explained in more detail in the document. The guiding principles state that decision makers incorporating coastal flood risk projections in any decision should support greenhouse gas reduction policies that help us avoid the worst of the impacts, so that help us stay on that RCP 4.5 scenario or even better. Use an approach that considers how tolerant the project is to flood risk, and we'll talk more about that in a few slides. Prioritize equity and justice for the most socially vulnerable populations among us. Protect natural, cultural, and historic resources and public access. Be bold, create a really bold vision and start now. But act in increments and also opportunistically as opportunities present themselves. Consider the full suite of actions that could be taken, including everything from not taking action, which is always an option, to figuring out how to live with the water, how to keep water out, or how to get out of the water's way. Be flexible with the strategies that are adopted and keep track of how they're working over time so that they can be adjusted if conditions change or if they lack the effectiveness you're looking for. Coordinate and collaborate a lot. And finally, keep in mind that there may be some liability of not taking action if you have scientific information in front of you that does suggest that action should in fact be taken.
So the next section of the guidance lays out what I like to think of as the real meat and potatoes of the guidance, or the step-by-step approach for selecting and incorporating the various coastal flood risk projections into your decisions. The 7 steps outlined here are intended for everyone from property owners to state agency staff, really anyone who is going to be making decisions about how to deal with coastal flood risk in the future, whether that means you're renovating your house, you're creating a community master plan, or you're setting state standards for road design or wetlands protection, for example. The guidance refers to the people making these decisions as decision makers, and that could be a multi-stakeholder group or even an individual, depending on the type of decision being made. Briefly, just to recap, the 7 steps include 1, defining your project, 2, determining tolerance for flood risk, 3, selecting your sea level rise numbers, 4, factoring in coastal storms, 5, identifying expected changes in groundwater levels, 6, identifying expected changes in extreme precipitation, and then 7, pulling all of that information together in order to evaluate cumulative coastal flood risk and come up with some management or adaptation options. These 7 steps are presented in a sequential or linear fashion, but prompts are included throughout the guidance to encourage iteration. Meaning if you get stuck or you need to adjust something as the process progresses, feel free to go back and revise your responses to previous steps as needed. There aren't really any hard and fast rules that you need to follow. As mentioned earlier, this guidance is really just a voluntary framework to help you think about how to use the science. But if you have a different way to do it, whether that means skipping a step that may not apply to your particular project or employing a more sophisticated methodology to assess coastal flood risk, again, please feel free to do so. At the end of the guidance, I also want to highlight the fact that you'll find a worksheet that breaks down the steps into more detail. The worksheet is also voluntary, but it might be really useful to play around with, particularly if you have a specific project in mind that you'd like to apply the guidance to. We're now going to walk you through the 7 steps and are going to use a site-specific project example to help illustrate how each of the steps might apply in this particular circumstance. In some cases, we're briefly going to touch on how the steps might work for a planning or regulatory project, but given the time constraints tonight, we'll plan to focus more on those project types at future trainings. The steps, understandably, may seem a little bit more complicated for planning and regulatory projects, but I just want to point out that there's some really good detail in the guidance about how to think about all 3 project types, especially in the colored boxes called project-specific considerations and examples. So I'd encourage all of you to read through those in the meantime as we plan future trainings, and remember to jot down any questions that you come across or that come up for you so we can address those at those future trainings.
All right, so step 1 seems simple at first glance, but actually is probably the hardest one to tackle. The term project is used really broadly in the guidance to mean any private, local, state, and federal planning, regulatory, or site-specific efforts that should consider and incorporate coastal flood risk projections. Some examples of possible projects are included in the report and on this slide in that orange box, but that list is by no means exhaustive. Next slide. So in step 1, you're asked to define your project goal. One example used in the guidance is a project with a goal to build a new hospital. And then you're asked to define your project type. So building a hospital would be a site-specific project type. You're also asked to characterize the project area. If you're building a hospital, you'd think about the hospital site itself, but you'd also be thinking about the area around the hospital site that the hospital is intended to serve, and the area that the hospital depends on outside of the site, so road access and power lines, for example. This step gets a bit more complicated if you're dealing with a big area or for a broad project like a master plan or an update to existing floodplain regulations, for example, where the project area might actually be an entire jurisdictional boundary that you might think about breaking down into sub areas like zoning districts or Perhaps specific structures, facilities, and natural resources might need to be inventoried and categorized within that larger project area. So the guidance lays out how you might think about characterizing the project area for those types of projects in a lot more detail, as Nathalie suggested. Then finally, in step one, you're asked to think about the project time frame. So depending on the project, this might be your planning horizon for a master plan, or some type of regulatory time period if you're designing new floodplain regulations, for example. Or for your site-specific project, it would be your useful life. And useful life is the time period over which a project is expected to be available for use. It's typically longer than a project's design life, which is a term we're probably more familiar with. You also want to think about any major incremental action points within that project timeframe. So if you're building a hospital, the useful life of the project might be 100 years, but there also might be some important upgrades that you estimate would take place every 30 years. And those would be points of incremental action.
The next step, step 2, directs decision makers to determine their tolerance for flood risk. Now, we know from the public input sessions where we got feedback as part of developing this guidance that this concept can admittedly be a bit confusing at first, but it should come relatively easily once you get the hang of it. It's also a really critical concept to get the hang of, because what you decide in this step, step 2, informs everything that you do in the subsequent steps. You might find yourself back here partway through the process to reevaluate what you decided in terms of what your initial tolerance for flood risk might be, and that's okay. So let's first start with the definition. According to the guidance, tolerance for flood risk is defined as a decision maker's willingness to accept a higher or lower probability of flood impacts. And that willingness might be based on a variety of project characteristics. So things like project value or replacement cost, capacity to adapt, the importance of the project for public function or safety, and sensitivity of the project to flooding or inundation. So let's break this down for you a bit more. Let's think about 2 site-specific projects. One project is to build a walking path, and the other project is to build a hospital. Your walking path probably has a relatively lower cost. It's not that hard to move if absolutely necessary. It's not that important for public safety, and it can probably dry out and withstand some level of flooding. So for those reasons, that walking path project would have a high tolerance for flood risk. It can tolerate a high risk of flooding. On the other end of the spectrum, the hospital is relatively expensive to build. It's really hard to move once constructed. It's critical for public safety, and it might not bounce back as quickly if important aspects or components of it get wet. Therefore, the hospital project has a very low tolerance for flood risk. It cannot tolerate much risk of flooding. In step 2 of the guidance, you'll also find the step 2 table, which divides tolerance for flood risk into 4 categories to choose from: high, medium, low, and very low. It presents a much more detailed framework to help decision makers decide what their project tolerance for flood risk might be. You'll note that for planning and regulatory projects, and in some cases for site-specific projects, you might want to select more than one tolerance for flood risk for different parts or components of your project. And for regulatory projects that solicit applications for permits, in some cases, it might be prudent to predetermine tolerance for flood risk for specific structure or asset types, or alternatively, you might ask the applicant to justify their own tolerance for flood risk based on the guidance. You'll also note for the engineers on the line that the 4 categories of tolerance for flood risk correspond with the flood design classes that are identified in the American Society of Civil Engineers Flood Resistant Design and Construction Standard, otherwise known as ASCE 24-14, which is also incorporated into the existing state building code. So as you'll see in steps 3 through 6, the coastal flood risk projections that you select are going to differ greatly depending on the tolerance for flood risk that you select in step 2. This is going to allow for some really important flexibility and a bit of subjectivity throughout this process.
So step 3 directs decision makers to select the appropriate relative sea level rise number or numbers for their project and assess the impacts. Based on the time frame or timeframes determined in step 1 and the tolerance for flood risk determined in step 2, you can use the step 3 table, which is pictured here, to find the recommended relative sea level rise for the project. RSLR values provided in the table are lowest for projects with high tolerance for flood risk, like a walking path, and highest for projects with very low tolerance for flood risk, like a hospital. Next slide. So back to our hospital example, if the useful life is 100 years, so we're thinking about the year 2120, and tolerance for flood risk is very low, decision makers would plan for 8.3 feet of sea level rise by the end of the hospital's useful life. If an important incremental action point like replacement of key utilities takes place in 30 years, then decision makers might also think about how they could plan for 2.3 feet of RSLR when they replace those utilities in 2050. And that might help them spread out the costs of adaptation over time. Next slide. So the second part of step 3, 3.2, directs decision makers to assess how this RSLR affects their particular project. There are a number of methods and tools available to help you do this. Many of you are probably familiar with some of those, but a relatively simple tool to help you get started is referenced in the guidance. It's a sea level rise mapper. You can see the URL in the green box on this slide. And the mapper has a number of sea level rise and other flood risk maps on it. For the hospital, we might go to the mapper and see what 8 feet and maybe what 2 feet of sea level rise look like at and around the hospital project site. If the project area is impacted under those two scenarios, decision makers would note possible impacts, both to the site itself and to the surrounding areas that the hospital depends on or serves. Of course, with a project like a hospital construction, site engineering survey and other methodologies would be employed to get a much more detailed understanding of that relative sea level rise risk and the potential impacts to the project.
The next step, step 4, walks you through how to identify and assess RSLR, or relative sea level rise adjusted coastal storm impacts to your project, recognizing that coastal storms are going to occur on top of higher sea levels in the future. Before we get started, there are a couple of terms that I'll be using that I want to define for you just to make sure that we're all on the same page. The first term is freeboard, which is commonly defined as a factor of safety and is usually expressed in feet above base flood elevation for the purposes of floodplain management. That brings us to our next term, base flood elevation, or BFE, which is the elevation to which floodwaters are expected to rise during the base flood, otherwise known as the 1% annual chance or 100-year flood. BFEs are shown on FEMA flood insurance rate maps and on flood profiles. Both of these terms are really important to know in order to understand the meaning of design flood elevation, or DFE, which refers to an elevation above base flood elevation that incorporates freeboard or other adjustments like sea level rise to provide increased flood protection and minimize flood damages. The first part of step 4, step 4.1, is to determine the RSLR adjusted DFE for your project. The step 4 table, pictured here, demonstrates how to calculate RSLR adjusted DFE based on the tolerance for flood risk you selected back in step 2. In short, you're going to add the RSLR estimate you selected in step 3 to current BFE and freeboard requirements that are put forth in the ASC 24-14 standard I referenced earlier and incorporated into the New Hampshire State Building Code. These existing flood protection requirements are shown in the brackets in the table. I know that's a lot of information to digest, so hopefully an example will help illustrate what I'm talking about and clarify any questions that you may have at this point. So here's our hospital that we determined had a very low tolerance for flood risk, and that should plan for 8.3 feet of sea level rise by 2120. For the sake of this example, let's say that the hospital is going to be sited in the 1% annual chance floodplain in an AE zone with BFE of 8 feet and GVD. To calculate RSLR adjusted DFE, we're going to use the equation presented in the step 4 table that corresponds with very low tolerance for flood risk. This prompts us to add our RSLR estimate to current flood protection requirements of BFE plus 2 feet of freeboard. So if we add our numbers together, we get BFE of 8 feet and GVD plus 2 feet of freeboard plus 8.3 feet of RSLR, which equals an RSLR adjusted DFE of 18.3 feet and GVD. Once you calculate your RSLR adjusted DFE, step 4.2 prompts you to assess RSLR adjusted coastal storm impacts to your project. Again, one cursory way of doing this is to just visualize RSLR adjusted coastal storm water levels using the sea level rise mapper that Kirsten referenced, or employ more technical engineering methods depending on the project.
All right, so step 5. As Nathalie mentioned earlier in the summary of part 1, we know that groundwater levels are influenced by sea level as far as 3 miles inland from the coast. So for some projects, it will be important to understand how groundwater levels might change in the future as sea level rises, especially if you care about what's underground. So step 5 takes you through how to identify relative sea level rise induced groundwater rise, RSLR induced groundwater rise, and then it helps you to estimate depth to present day groundwater and to future groundwater, which is also referred to as RSLR adjusted groundwater. And finally, it helps you to assess the groundwater rise impacts to your project. So the step 5 table can be referenced to help you calculate your depth to RSLR adjusted groundwater. First, you have to determine the RSLR induced groundwater rise expected in the project area. So groundwater rise has been mapped for some coastal New Hampshire communities, but not all of them. And you'll start by consulting the list and the guidance to see if groundwater rise maps exist at your project site. If they do, you're directed to follow the preferred approach for mapped communities, which is in the center column of the table here. And that refers you to the sea level rise mapper to use the groundwater rise data layers associated with the RSLR values that you chose in step 3. This should give you a number or a range of expected groundwater rise for your project area. If your project takes place in an unmapped coastal community and is located within 3 miles of a tidal shoreline, you're directed to follow the alternate approach for unmapped communities, which is the right column of the table. And you'll calculate a range of possible groundwater rise based on the RSLR that you chose in step 3. The lower end of that groundwater rise range will be 33% of your RSLR, and the upper end of the groundwater rise range will be 66% of your RSLR expected at your project location. Then next, you calculate the depth to your RSLR adjusted groundwater. So whether you're in a mapped community or not, you'll subtract the groundwater rise amount or the range of groundwater rise that you came up with from your present day depth to groundwater. And that present day depth to groundwater is determined using best available information. Some possible methods are noted in the report. All right, so let's go to the next slide. And let's look at this through the hospital example again. So we'll assume that the hospital project is located in a mapped community. And when we took a look at the sea level rise mapper, we found that groundwater rise at the project site is expected to be 5 feet, based on the 8 feet of RSLR that we're using for that site. We know that based on test pits at the site that depth to present day groundwater is 4 feet. And so subtracting expected groundwater rise from present day depth to groundwater, we get -1 foot for the RSLR adjusted depth to groundwater. And so that negative value here actually indicates that under these conditions, the groundwater would actually be rising above the surface, land surface, by 1 foot, causing surface water inundation from that change in groundwater levels.
So step 6, moving on, prompts you to first account for projected increases in extreme precipitation based on your tolerance for flood risk, and then to assess potential impacts to your project. In general, step 6.1 directs you to account for a 15% increase in extreme precipitation estimates if your project has a high to medium tolerance for flood risk, and to account for greater than 15% increase in extreme precipitation estimates if your project has a low to very low tolerance for flood risk. Now, planning projects may account for this in a more qualitative manner, whereas projects involving detailed hydrologic and hydraulic modeling are advised to increase best available extreme precipitation estimates that you can get from the Northeast Regional Climate Center or NOAA Atlas 14 by 15% or greater than 15%, depending on the tolerance for flood risk of the project. So this is largely consistent with the guidance that was put forth in the 2014 science summary, and that has since been incorporated into current state alteration of terrain program regulations. So many of you are likely already familiar with how to incorporate these projected changes in extreme precipitation into your stormwater drainage analyses, for example. But for those of you that might need a refresher, here's another example. Let's say that the storm duration and recurrence interval of interest for our hospital is the 24-hour 10-year storm event, which according to the Northeast Regional Climate Center data is expected to produce 4.9 inches of rainfall at our project location. Given that our hospital has a very low tolerance for flood risk, I'm going to consult the rightmost column in the step 6 table and multiply my present day extreme precipitation estimate of 4.9 inches by greater than 15%. So say for the sake of this example, the decision makers involved want to take a precautionary approach and decide to plan for a 20% increase in extreme precipitation. We would then multiply our present day estimate of 4.9 inches by 1.2 to get a projected extreme precipitation estimate of 5.9 inches. Decision makers would then evaluate how this increased precipitation might result in increased runoff at our site, freshwater flooding, or even how it might combine with saltwater flooding to impact the project site. Again, this could be done in a number of ways, in a more qualitative way, for planning level projects, or it could be assessed using more technical engineering methods and models.
So we've made it to step 7, and there's unfortunately no magic cumulative equation to help us wrap up all of this in a box and tie a bow on it and call it done. Stakeholders ask for that, and we wish it existed, but it doesn't. That said, step 7 does guide decision makers as they try to understand cumulative impacts of the 4 coastal hazards that we've looked at in steps 3 through 6, using either advanced quantitative approaches, if those are available to you and resources allow, or qualitative methods that are more accessible. And then it also helps folks come up with some options. So step 7, table A, describes 5 types of action that decision makers should consider And thinking back to the guiding principles, remember it's important to at least consider the full suite of actions available before picking what you think is the best alternative. The 5 options include no action, avoid, accommodate, resist, and relocate. And in other words, that means don't change anything, put the project somewhere safe from flooding in the first place, figure out how to stay put and how to deal with getting wet, figure out how to stay put and stay dry, or move out of the water's way or create conditions that facilitate the natural migration out of the water's way over time. Next slide, please. So step 7, table A, offers some additional guidance about what actions might make the most sense for your project based on the project's actual coastal flood risk and tolerance for flood risk. Can you hit the next slide button? Thanks. When building a new hospital with a very low tolerance for flood risk, the options that probably make the most sense are avoiding, resisting, or planning to relocate it over time. Obviously, for a new hospital, if you have the flexibility to select a site that is high and dry to begin with, that's probably the best way to go. But depending on the project, decision makers are potentially going to employ multiple types of action over time. And the step 7 table B, which is in the guidance as well, offers more action ideas to help you brainstorm and get creative. The worksheet also has some useful tools and tables that you can play around with when you're trying to populate your app options for step 7 and for some of the other steps, as well. Next slide. So how should you be thinking about using the New Hampshire Coastal Flood Risk Summary and more specifically the guidance in your own respective contexts? If you're in a coastal New Hampshire community, the guidance might be applied to your own property, to your neighborhood, to places that you care about, like the beach, for example, or for projects that you work on. Coastal community representatives and state agency representatives should consider adopting the guidance or using the guidance or relevant aspects of it in plans, in regulations, and in investment decisions that they manage or oversee. And then finally, we do expect the guidance or parts of it to be used in some state decision-making, including permitting at the Department of Environmental Services and in design work at the Department of Transportation, just to give a couple examples. The Department of Environmental Services wetland rules were updated, and that went into effect in December of 2019, as some of you know. And the coastal rules presented in Chapter 600 require a vulnerability assessment that includes consideration of sea level rise, coastal flood risk, and some other factors. The permitting worksheet associated with the vulnerability assessment does reference this guidance document. And the Department of Environmental Services alteration of terrain rules also require consideration of future coastal flood risk. Nathalie mentioned their requirement for future extreme precipitation. They also require coastal flooding, sea level rise in relevant permit applications. So the guidance could be used to fulfill the requirements there.
So if you're still with us and wondering where to find additional information, we encourage you at the very least to read Part 2, the guidance, if you haven't done so already. A recording of this webinar is also going to be posted online, and you'll be notified when it's available to view. And then, as we alluded to earlier, we are really still planning to hold additional in-person trainings in the future once the public health crisis has subsided. So please keep an eye out for more information on those, hopefully coming soon. Print versions of the guidance are going to be available in early April or early to mid-April. And we have plans to disseminate those to municipal staff and various boards and commissions in our municipalities. But if you would like your very own hard copy, please contact me and I will be pleased to send you one. And then finally, and perhaps most importantly, Please don't hesitate to get in touch with me or Kirsten if you have any questions immediately following this webinar or several months from now. We are always happy to schedule consultations upon request, especially if you have a specific project in mind that you'd like to apply the guidance to. So with that, I just want to thank you all again for your attention and participation on this webinar this evening. We're more than happy to take questions now and respond to those that we don't get to or can't answer at the moment in writing following the webinar. So I'm going to turn it over to Abigail, who's going to facilitate the Q&A.
Terrific. Thank you, Kirsten and Natalie, for the presentation. We just have a little bit of time for a few questions, so we can get started. The first question is, if utilities are buried, does or can this process rank the sensitivity of various types? And I believe various types is referring to the different utilities.
Yeah, so you would definitely need some additional information about the vulnerability of the utilities themselves to flooding. But once you have that, you'd be able to determine the tolerance for flood risk of those utilities that you're burying. And you would be able to use this process to figure out, based on the design life or the useful life of those utilities, what sea level rise and groundwater rise you would expect for the sites where those utilities are located, and then make some decisions about, which ones might need replacement first and how you might want to replace them so that they're resilient into the future, to the time frame that you're looking to have them operational for. Hopefully that answers that question, at least to start.
We have a question regarding step number 4. I'm wondering if you two would take a moment just to discuss what you might suggest for the hospital, and whether the hospital would have to be built at the 18.3 feet above base flood elevation.
So I can respond to that question, Abigail. That 18.3 feet actually incorporates BFE. So that's the total elevation to which the guidance recommends the hospital should be built to. So it's not above base flood elevation. It's 18.3 feet NGVD 29, which is the reference datum on our current floodplain maps. So to answer the specific question, it's not above base flood elevation. It actually incorporates the base flood elevation into that total design flood elevation.
Great. Question number 3, there's some curiosity about how this information is used in relation with the FEMA flood maps.
Yeah, so that's a pretty big question, but it can give it a try. The information presented is very relevant and very possible to be used with FEMA flood maps, especially if you're in a coastal area or within 3 miles of a tidal shoreline. So if you're thinking about your flood zones on your FEMA flood maps, the step 4 that Natalie was just recapping would be probably a good place to focus, because a lot of that step tries to sort of add future flood risk from sea level rise to the kind of existing floodplain management realm that FEMA flood maps kind of operate in. So that would be kind of a good place to focus. And essentially, one starting point concept is that in step 4, you're basically told if you have a base flood elevation on a FEMA map, and you expect sea level rise at some point in the future that you're interested in planning for in that area, you would add that sea level rise that you're expecting to that base flood elevation that you're dealing with today in your flood zone. And that would kind of be a rough estimate of where you'd expect a future storm to kind of flood, and the depth at which you'd expect the future storm to flood in that area. Again, it's kind of a rough estimate. There certainly are other kind of dynamics that you have to get into when you think about water moving and at different depths in coastal areas, and so there's a lot of options there for how you might approach that.
Okay, I'm going to try to squeeze in one more question. Do you see this guidance being used in capital improvement program or CIP preparations?
Yeah, I personally do, definitely. I think this is a great tool for communities to use when they're evaluating projects or designing projects as part of their CIP process. So I think that's a definite yes from me. Kirsten, I don't know if you have anything to add.
Yeah, I mean, I might point you to the step 7 table B that we talked about there, a bunch of different kind of project types that are listed there that may give you some ideas for the different specific local and other site-specific decisions and projects that may be employing this guidance. And so site and subdivision planning and regulations, capital improvement planning, a lot of other kind of planning approaches and investment frameworks are definitely on the table.
Well, unfortunately, we do not have enough time to address all of the questions. We have just 3 more. So as was mentioned earlier, we will compile answers to those and provide those electronically following the webinar. Now to wrap up today's webinar, I will pass over to Amanda Stone.
Great, thanks Abigail. And thank you everybody for participating on this webinar tonight. It's been great having you all here, even if we could not see you, but at least you were able to see some of us. So before you leave, we have a quick exit poll like we did earlier. If you can just click on it before you move off, that'll just be helpful to us. So just click on the appropriate response as you did earlier. We are going to be sending out an electronic evaluation survey by email, so please complete that, because that'll be very helpful to us as we determine what additional support, training, and other information that you might need. So you'll get that either later today or tomorrow morning. Keep clicking on that exit poll. Enjoy the rest of your evening. Stay well, and thank you for being here tonight.